My name is Liz.
My name's Jordan. We're both civil engineering students here at New Mexico Tech. For those of you who haven't heard of civil engineers, they have a hand in designing all parts of life, really. If you've ever walked on the sidewalk or been with your parents as they drove over a bridge or turned on a sink, I mean, odds are civil engineers have had a hand in designing some of those things, and that's what we're studying today. So we have a little bit of a demonstration here that we're going to teach you about a little bit of physics and some engineering, and Liz is going to describe our little experiment going on.
Okay, so today we're going to do a little activity, and like Jordan said, it's a little bit of physics and engineering put together. So you guys are going to make little foil boats, and Jordan and I both have one that we made beforehand to kind of give you an example. We're going to take these boats and we're going to put them in tubs of water that we have in front of us right here. You guys don't have to use a tub of water, but we'll talk about that in a second. So then we're going to take marbles, and we're going to see how many marbles or how much weight it takes to sink this boat. We need you guys to go get a few things from your homes, and then Jordan's going to talk about that.
Start? Okay. So first off, what you're going to need is a small sheet of tin foil. This is about 1 foot by 1 foot. So if you have a ruler, it's about the length of one of these. So if you can just cut a square like this, and this is what we're going to be folding into the boat. And as I mentioned, you're also going to need a ruler. You're going to need some sort of small tub or like a sink or something you can fill with water to place your boat in to have it float. Also, as Liz mentioned, you'll need some type of weight. Here we have marbles. You can use loose change. If you have marbles, you can use those, or anything small and heavy, sort of dense that you can use to weigh the boat down. You'll also need a small calculator, kind of like this one. It might help with some of your math. And other than that, that's about it.
So we're going to give you guys a few minutes. We have a list on the board of things that you need just in case you forget. If you're on a tablet or a laptop, it's a good idea. If you don't have a bucket or a bowl to put your boat in, and you're using a bathtub or the kitchen sink, you can take us with you on your tablet or your laptop, and then you can do the activity with us. So we're going to give you a few minutes, and we're going to show you guys what you need just in case you forget, and we'll see you in a few minutes when you're done getting your stuff.
I think some people should have all the stuff because it's listed, so I don't think we'll need to like too long.
Okay, so hopefully you guys were able to grab everything that you needed. I'm going to show you guys first how to calculate the area of the sheet of foil that you have, and we're not actually going to use this, it's just kind of a good practice calculation. And then I'm going to do a little demonstration of a boat really quickly, and then Jordan can show you how to calculate the volume of your boat. So what we're gonna do for the area, and your area might be different from my area, and that is okay, because it's just gonna depend on how big your sheet of foil is. So if you have a ruler, that's great, you can use your ruler. If you have a tape measure, that's fine as well. I'm gonna use a tape measure because it's easier for you guys to read on the camera. So I'm gonna take the length of the two sides. So my foil is almost 12 inches. It's about 11 3/4 of an inch. Yeah, I can remember. So 11.75 inches. And then the other side is about 13.5 inches. And these don't have to be, there's lots of little tick marks on your ruler or your tape measure, and they don't have to be perfect. Just to the nearest 1/4 of an inch or 1/2 an inch is fine. So that's how you calculate the area. So I'm just going to fold this. Oh, 13.5 inches. So let's go ahead and calculate the area because I forgot to do that. So I'm going to try to do this upside down so you guys can see it. So I have 11.75 inches, and I'm going to multiply that by the other dimension, which was 13.5 inches. So the area of my boat, or excuse me, of my foil, is 158.6, which is just over 158.5 inches squared. So that's how you calculate area. And then I'm going to do a little demo boat. You don't have to make one that looks like this, but you are welcome to. I'm just going to fold up the sides. And you don't have to make it the same size. You don't have to make it the same shape. Later, we're going to talk about what might impact how quickly your boat sinks or how much weight it takes to sink your boat. But for now, we're just going to smoosh it into a shape. It's not high tech. We're just smushing stuff together. And the boat that I'm making right now looks different from the boat that I made to use for the demonstration, but that's okay. If I can remember how to make it. There we go. And the good thing about foil is it just kind of smooshes together. But if you have tape, you can also tape it. That makes it what's called water fast. And then you won't have a leak like the Titanic did. Your boat won't sink quickly. So it's just a little rectangular boat. You don't have to make it look like that, but that's what I have. And then Jordan's going to show you how to get the volume of the little boat.
Alrighty. So once you have your boat made, we're going to use this one as an example. So here, basically what we have is, you can kind of think of it as a small box. And the first two measurements we're going to do are extremely similar to the first one that Liz did in the beginning, where we're going to measure the short side or one long side or either or of your boat. And you're going to take this measurement and you're going to record it. So here we have 4 inches. So that'll be the first length of one side of our boat. And then, just as we did before, we're going to measure the next side. In this case, it's the longer one, and it's about 9.5 inches. So if you multiply these together, you would get just a flat area, like if you were just looking at this flat area of the boat. But what we want is the volume. So what we're going to have to do next is measure the height of the boat. So in this case, we're going to take, let me do this better. We're going to take our tape measure, we're going to put it vertically, we're going to put it upwards, and then just read off the height as you did before, which in this case is about 1.5, my bad, 1.5 inches. So there we have a length, and then the height of our boat. And then if we multiply all 3 of those together, we should have a volume. So in this case, we're going to do 4 inches times 9.5 inches times 1.5 inches, which is 57 cubic inches. So that's, if you were to take a 1 inch length and make that into a box, There's 57 of those that would fit approximately within this boat here. So there's your boat volume.
All right, so we have our preliminary calculations. Now we're actually going to put our boats in our water, and we're going to put our marbles in. You're going to put in whatever you guys are using for your weight, and we're going to see what it takes to sink our boats. So go ahead and get your boats and your water. Jordan, get your water.
My water?
Yeah.
Oh, yeah.
That's my water.
That's right.
All right.
Should we ask them if they have any questions about boats?
Do you guys have any questions right now? Is anybody confused? Or are you ready to put your boats in the water? Don't see anything. I think we're going to go ahead and go ahead. Go ahead and go ahead. We like math, not words. Okay. Chips ahoy.
Ships ahoy.
We have our boats in the water. We're going to put our marbles in. I'm just going to take a little handful here. And we want to slowly add the weight, because if we add it really quickly, then that could sink the boat. And you could think about, what happens if you put all your weight in the center of the boat? What happens if you put the weight evenly over the boat? What would happen if you put all your weight in at the same time? So like if you had a trampoline and you jumped on the trampoline, you would bounce back up again. If you jumped on this boat, it would not bounce. It would sink. But if you step on a trampoline, you don't bounce, right? So the slower that you get into a boat, the slower or less likely. So you can see it's already starting to go under. It hasn't sunk yet, but it's getting there. I've lost my marbles. I don't know if anybody knows what that means, but it means I've gone crazy.
Before their time.
So we're getting there. We've got one side that's sinking. Get back in the center, dude. My boat's being stubborn. It's very sturdy. Some of you,
Yeah, you made a good boat.
it's because I'm an engineer. Some of you may already have boats that sink, and that's okay. The whole purpose of this is to just see what happens. So that's what science is, and that's what engineering is. We just want to see what is happening, and well, civil engineers, we want to protect people. So all of my marbles are about to drown, but that's okay. I'm going to start adding it a little bit faster just because I have the whole surface area of the bottom of the boat covered at this point. And I can tell I've sprung a leak. I see it. We're about to go under.
Taking on water.
The structural integrity of my boat is not sound anymore. We're very, very close to sinking. Right at this corner is where we're going to go under. Even if I put things at this side.
Oh no.
Oh, no.
There we go. And we've
Oh.
sunk. So now what we need to do, it's going to be cold. We're going to take whatever you used to sink your boat. If you used change, that's great, because Jordan and I actually looked up the weight of loose change. And so you can, or the mass of loose change, you can use that to calculate the mass that it took to sink your boat. But I'm a little wet, so I might let Jordan do the writing and the electronic stuff now. So we are not going to use, we can do a demonstration calculation if you guys use change, but we're going to use a little scale to figure out how much weight it took to sink our boat. If Jordan doesn't break it.
Oh. I thought I did break it.
No, it's fine. Do you need some? I can write this later. Actually, do that right now.
I think he went out to get paper towels for
Oh,
you.
okay.
Just letting you know.
Okay.
Alrighty, so I'm going to calculate the mass of these. Alright, so what we're going to do is right here we have a little scale. as you can see, if we fill this up with our marbles, it's going to press that down, and it's going to give us a measurement, in this case, either in grams or ounces. So we're going to take all these marbles that we put in the boat, and we're going to slowly add them to this, and then we're going to tally up the total mass measurement, and we'll use that for our calculation. Alrighty, that's all of our marbles. So now, if we look down here at our scale, we can see that, what do you want in grams? Grams and ounces. All right, so we're just going to read this scale here. It's going to have these little tally marks, and it looks like it's about 400 grams. So Liz is going to record that for us. Oh, we have one more.
Oh.
I don't know how much that'll affect it. It's still about 4,000.
1,000 grams?
Or no, 4,000. 400. Yeah. Sorry, not good numbers or words. 400 grams is
400 grams is what we have. That may not be what you have. So if you used coins, then we can show you really quickly how to figure out what the mass of what the mass was that required your boat to sink. Mass is a little bit different from weight, but we don't really need to talk about that too much. Mass is how much of something you have, and weight is it's because of the gravity. So like if you jump up in the air, Earth's gravity is pushing you back down. And so weight is just the amount of stuff that you have multiplied by the force of gravity that shoves you back down or shoves the marbles back down on the Earth. That's why they're not floating. And that's why people float in space, because like on the moon has less gravity than the Earth does. It does still have some though. So right here, Jordan did the honors of looking up the masses of all the different coins that you might have. So if you want to find the mass of what it took to sink your boat, you just need to multiply the number of quarters or dimes or nickels or pennies that you have by the mass. So this first number is the mass in grams, and this second number is however many of those coins that you have. I don't know how many you have, but I trust your math skills. And so you just multiply these two together. You're welcome to use your calculator. So let's say you had 4 quarters, 5 dimes, 6 nickels, and 7 pennies. I just threw those numbers out. So your mass would be 5.6 grams. Let's use units, they're important. Times 4 quarters, and I'm just going to put a 4. I don't have to put quarters. You can put quarters if you want to, but I'm trying to go a little bit faster so that you guys can do your activity and not have to focus on what I'm writing. So 5 dimes, and I'm going in this order right here, plus 5 grams times 6 nickels. I feel like I'm really low to the ground right now. 2.5 grams times 7 pennies. And then so you would just, if those of you who have learned about order of operations, or please excuse my dear Aunt Sally, what we're going to do is we're going to multiply first, and then we're going to add. So we need to multiply all of these things together. So we have 5.6 times 4, which is 22.4. I'm just going to write it right above. Can you read that? Is it too small? I think we can. Here, I can just write it right below. We'll do that. So right now, I'm just multiplying these things together, and then I will add them. 2.3 times 5. My calculator is not playing nice right now. There we go. 11.5. 5 times 6 is 30, so that would be 30.0. These are all in grams. That's the engineer in me trying to put units on things. And then 2.5 times 7, 17.5. And we add all of that up, and that is going to give us the mass that it took to sink this example boat. This isn't going to be yours. 5 plus 30, so it's 81.4 grams. If you want to figure out what that is in weight, or what the weight of that is, you would just multiply that by gravity, and that would give you the weight. Gravity is 9.81. We don't have to worry about the units on that. That's if you're using the metric system. Here in the US, we use the imperial system. It would be different units, so you need to make sure to use this number if you want to find out the weight. But here in the US, we use a different number, 32.174. And that will give you the weight in pounds, but you need to use this number for this calculation because the units match. But that's only if you want to. Okay.
Do you want me to compare different shapes?
Sure. So before we do the last calculation, that's the entire purpose of this, which is to calculate the buoyancy force, Jordan's going to do a little demonstration of a different shape boat and how much it might take to sink that.
All right, so as you saw in our first demonstration, if you have a square, you can have this is sort of a rectangular box or something. So you can have a square boat like this, but there are other variations of shapes you could use too. Like for example, I just kind of made this one into a circle. And then this one here is sort of shaped like a triangle. Now, each one of these, if you were going to calculate, say, the area or the volume, the calculations would be slightly different just because it's a different shape. But because the areas are different, that might have a completely different effect on the boat itself and its ability to float whenever you add water to it. So we haven't tested these. I think we'll probably move on to the calculations after this, but I just wanted to show you guys that there are other variations of boats that you can use. I mean, you see all different shapes and sizes. You see aircraft carriers or cruise boats or just small sailboats that are sort of triangular, more like this one. And they all have different properties whenever they're set in the water. So on your own time, if you're interested, you can go ahead and fold yourself some different shape boats, some different sizes, and compare those and see which one floats better, if they're similar sizes or how that surface area affects the amount of weight it can hold in total. So that was just another little topic. Like I said, there are two little demonstrations here. I like the triangular one. I think it's pretty cool. And personally, I think it would work better than the square one, but
It's because he made the triangle.
it's because I made the triangular one. So other than that, we're going to go ahead and move on to our buoyancy force calculations. So
Okay, so when you go swimming, I'm sure you guys have noticed that you float in the pool, or some of you float. I, for some reason, do not float. I'm not a very buoyant person, evidently. But the whole purpose of this activity is to figure out what the buoyancy force is. So, and this is for your boat specifically, so it's going to be based on the volume of your boat. So to calculate the buoyancy force, which is the upward pushing of water against whatever is in that water. So we're going to take, so this is the force due to buoyancy, that's why there's a little b there. It's going to be the volume times, this is a Greek letter, you don't need to worry about it. It stands for density, and then this little g is for gravity. So the density of water, you do need this number right here. It's 0.03611, and that is in pounds per cubic inches. So what I'm going to do is I'm going to calculate the buoyancy force on our boat using our boat volume, and you're going to do it for your boat volume. So the volume of our boat was about 57 cubic inches. So our buoyancy force is our volume times the density of water. And the density of salt water is a little different, but I'm guessing that you're using fresh water at home, so we're just going to go ahead and use this one. 0.03611 pounds per cubic inches. And then we're going to multiply that by gravity, which is, that should be a 3. 32.174. No, because we're in inches. It's like
yeah,
3 something. Yeah.
Do you want me to look?
It's okay, I can do it. Feet per second squared. So I'm going to need to convert this into inches really quickly. So they're 1 foot has 12 inches. And this is really important. I'm so used to using that notation. Because our units won't match, and we want units to cancel. So when you start, whenever you guys become engineers, and you start doing these kind of calculations, you know you did it right if your units cancel. So I have inches cubed and inches cubed. This is multiplying and then dividing, so those are going to cancel. Then I have feet and feet. Those are going to cancel. And so now I'm just going to grab my handy dandy calculator, multiply all of this out. So I have 57 times this little bitty number, 0.03611, times 32.174, and that's multiplied by 12 inches because we need it to match. So our buoyancy force is 794, we'll call it 95. We'll round up. We're civil engineers. We do a lot of that. It'll be pounds, inches per second squared, which sounds a little weird, and that's because of the system that we use here in America. So this is a force. That's how you represent a force in the system of units that we use here, which is the imperial system. I don't know if you guys have ever heard of the metric system, but in the metric system, that would be in newtons. Why do you care about what this is? So there's a very famous scientist, his name is Archimedes, and he realized one day he was taking a bath because he was stuck on a problem. The king where he was at, I'm pretty sure this might have been in Italy, it might have been in Greece, but the king thought that he got swindled on the gold that was provided for his crown, and he thought that it wasn't solid gold. And so he wanted Archimedes to figure out whether the crown was solid gold, but he didn't want Archimedes to damage the crown. So Archimedes was stuck and he didn't know what to do, and he did what good engineers do and what good scientists do when they get stuck, and he took a break. So he took a bath, and he noticed that when he got in the bathtub, and I'm sure you guys have noticed this too, that the water moved. It moved up. And so that's water displacement. And the larger something is, the larger volume it has, the more something is going to displace. And you can use that displacement and the mass of whatever you have, or I'm sorry, not the mass, the weight of whatever you have. It's been a long day already. You can use the density of water and the volume of your item to find out how much something weighs. And Archimedes knew how much gold weighed, or he knew the mass, so he was able to figure out if it was solid gold or if it was cut with something else. So he shouted, "Eureka!" Like, there is a relationship between the volume of water and the volume of an object that you place in the water, and so that is why you care about buoyancy force. Hope you had fun. I hope you all enjoyed the math that we did here, and that you all grow up to be very, very smart scientists and engineers and mathematicians and physicists.
Yeah, sure thing. Thank you guys. Thank you all for having us. We really hope this. We really hope this gets you excited about mathematics, about engineering. You know, it seems a little bit intimidating, but it's actually a whole lot of fun.
Very fun. Very rewarding.